Hey, in this screencast, I want to talk to you about forces as they apply to systems of objects. And it's kind of an important topic. It's one that takes a little bit of time to wrap your head around. You're going to do some practice. So I'm going to ask you to pay close attention, take notes, ask me questions in class, devote yourself to solving these problems, and you will get good at it, but it might take a little while. So let's get on it. Okay, so here's the idea. The universe is this really big place full of lots of things, and as physicists, we want to try to get a handle on the rules that govern how these things interact with each other. So, what we do is we define systems. So, a system is simply a part of the universe that's smaller than the rest of it. I'm just going to define a series of objects and say these objects are all I'm going to consider in isolation from the rest of the universe, just to try to see how it is that they interact with each other without confusing myself with all the other objects out there. And it really works. It's why physics has moved forward, is because this idea of using systems as a way of simplifying. So consider this. I've got someone playing pool, right? I've got a person, I've got a cue stick, I've got a pool table, I've got all these pool balls, I've got air molecules. But I'm saying, you know what? I'm just going to simplify the system and say all I really care about is this. I've got the cue ball. I'm going to call it B1, and it's in motion. And I've got this two ball. I'm just going to call it B2, and it's at rest. And those are the only two objects I'm going to consider to be part of my system. Everything else is external to my system. And that way I can just study how they interact with each other and maybe broaden that and apply it to larger systems. That's the way we do this. So here you go. I've got a system here. This system is just going to be comprised of two objects, a 4 kilogram box and a 2 kilogram box. That's my whole system here. All right. The floor is not part of it. The person's not part of it. The world's not part of it. Just these two boxes. Now, the first thing to keep in mind is this. Forces that are exerted between the objects that make up a system are internal forces to that system. And internal forces are always going to result in action reaction pairings. So, in other words, if this box pushes on this one with 4 newtons, then this one pushes on that one with 4 newtons in the opposite direction. Newton's third law. You can't push a box one way with 4 newtons without that box pushing the other way with 4 newtons. And because this is positive 4 and this is negative 4, that sums to 0. So the sum of the forces is 0. The sum of the internal forces is always going to be 0. And therefore, it's never going to cause the system to move, which is really what Newton's third law all comes down to. Okay. Now, let's see what happens here then. What about external forces? So external forces means forces between the objects in our system and things that are outside of our system. So what's outside of our system? Well, this dude is outside of the system. So this person's the force that this person is applying. This applied force is outside. Gravity's pulling down on these boxes. So the earth is outside of our system. The floor is pushing up. That's outside of it. All right. There's friction with the floor. That's outside of it. All right. So therefore, if I go ahead and make a free body diagram, here's what I'm going to get. I have my system has a mass of 6 kilograms, so mg is going to be 60. The floor is preventing it from sinking down. I wasn't given any information to assume that it's accelerating upwards or downwards. It's not in an elevator. We'll get to that later. So the upward force is 60, which is always going to be the upward normal force is always going to equal mg unless we have vertical acceleration. All right. Now these two forces are balanced, right? So since the mg down and the normal force up are equal and opposite, even though they're not internal forces, but they're still balanced, I can ignore them because they're not going to result in acceleration. All right. But if I look at the other forces, they're not balanced. So here I have a 12 newtons of applied force to the system and 4 newtons of frictional force acting in the opposite direction. And those are not balanced. So they are going to cause acceleration in this dimension. So I'm going to call right positive 12, left negative, that's 4. So negative 4 plus 12 gives me, 8 divided by 6. The whole system of two objects will be accelerating at 1.33 meters per second squared. And this is important because armed with this piece of information, I can start to answer things about individual objects within the system. So a common thing to do is determine which forces are balanced, ignore those, look at which ones are not balanced, consider how those cause your system to accelerate, and then use that to solve for other force problems that are being asked of you. So like we're going to do here. So we're going to use the sum of the forces equals ma, Newton's second law, to solve almost all the problems in this unit. We can have two different things. We can have static systems, one in which there is no acceleration. So here I've got these two boxes sitting on a floor. The floor is not in an elevator, so it's just at rest. Well, if it's at rest, the sum of the forces is definitely 0. It's not accelerating. It is in an elevator, and this elevator is moving upwards at a constant rate of 5 meters per second. Well, if it's not accelerating, even if it's moving, the sum of the forces is still zero. So it's still basically a static system. It's not accelerating. On the other hand, here I've got one where there's an applied force to the system in the x direction, and it is causing an overall acceleration. In that case, instead of the sum of the forces equaling zero, they're going to equal ma. And I'm going to want to figure out what that is in order to figure out the overall force on the system so I can do for you by diagrams on each of the objects and answer questions about them. So let's just try this here. I have a static situation here where I've got these boxes that are just balancing. What I want to do is I want to draw a free body diagram for the system as a whole and for the individual objects in it. Okay, so let's start with the whole system. It's got a mass of 6 kilograms, so mg is going to be 60. And since I'm told that it's not accelerating, I know that the net upward force is also 60, so the normal force is 60. Done. Okay, sums to zero. Now what I'm going to do is I'm going to go to the top box. I'm not the middle box is the tricky one, so I'm going to go to the top one because it's going to be easier. So I'm going to say, well, mg is pulling down on this one with 40 because it's got a mass of 4. So the mg down is 40, and it's not accelerating. So therefore, the upward force is 40. Now I've labeled it normal force, but in this case, the normal force is not caused by the floor surface, but rather this box's surface. So this one here, it turns out, is an internal force. I still have to diagram, but it is an internal force, which means it's part of an action-reaction pairing. So now when I go to do this one, I have to consider this force also. So I have 2 kilograms. My first go-to is mg. 2 times 10 is 20. I've got 20 newtons of downward force caused by gravity pulling on the object. All right. But I also have the fact that this pushed up on this box with 40, so this box pushes down on this one with 40. So I have 40 newtons in the downward direction caused by that box. You could say, well, you got 40 newtons sitting on top of it and it's pulling down. Okay, you could do it that way as well. But when I sum this up, what I get is 60 newtons, and it's not accelerating. So I know that the floor here is pushing up with 60 newtons, which, by the way, is what I said over here when I just look at the system as a whole. Okay. Now let's look at one where it's in motion and do the same thing here. So now I'm told that the system is accelerating. The person is applying a force to this 2 kilogram box, which is then applying a force to a 4 kilogram box. And the system of two objects is accelerating at 3 meters per second squared. So usually what's going to happen in these situations is either one of two things. You're either going to be told how fast it's accelerating, from which you must find the force, or you're going to be told the external force from which you must find the acceleration. It usually works out to be one of those two ways. So again, I'm going to use the sum of the forces equals ma. Well, there's no sum here. There's just this one force because, well, here, let's just try. We're gonna look at the system as a whole. So the system as a whole is 6 kilograms. So mg is 60. So the normal force up from the floor is 60. Now, if I have 6 kilograms accelerating at 3, 6 times 3 is 18. So I know the net force in this direction is 18. Now, let's move to this box here. Now, think about it for a second. The net force on this box can't be 18 because 18 newtons acting on 4 kilograms makes it accelerate faster than 3. So it can't be pushing that hard. So what happens is I go, all right, now what I'm going to say is, all right, I got 4 kilograms, so the downward force is 40, and therefore the upward normal force is 40. How much force is being exerted by the 2 kilogram box on the 4 kilogram box? Well, everything in the system is accelerating at 3. So I'm going to use this on this object and say F equals ma. 4 kilograms accelerating at 3 means the force on it is 12. There's a 12 Newton force pushing this box in this direction. That's why it's accelerating at 3. And that force is being caused by the normal force between these two boxes, which is an internal action-reaction pairing. So therefore, when I go to look at this one, I'm going to say, all right, 2 kilograms means I've got 20 newtons of downward force. It's not sinking into the floor or accelerating upwards, so the normal force upwards is 20. Again, they balance out, they often do. Then I go, well, I know that since this one was pushing this one with 12, then this one must push the opposite direction with 12. That's the one students often forget. Okay. And I know that this guy is pushing it this way. I've already figured out with 18. So I put that here. Now look at this 18 in the positive, 12 in the negative. What's that give me? It gives me 6 newtons, which is exactly what I would need in order to get 2 kilograms of matter to accelerate at 3. It's so cool. All right. Oh no, Mr. Sampson. What, three? Yes. Now we have three boxes. Okay, I have three boxes pushed across your welcome a frictionless floor, and they're accelerating at 2 meters per second squared. I want to draw a free body diagram for all three boxes. So the collective mass of the system is 8 kilograms. So that means I have 80 down. I have 80 up from the floor. They cancel each other out. And if I have eight, I'm going to use F equals ma to figure out how fast it's accelerating. It's accelerating at 2. The mass is 8. So that means I have 16 newtons of force acting on it, causing it to accelerate. All right. So that's how hard this person is pushing with 16. Now I want to do a free body diagram for just a system that's only comprised of boxes B and C. Okay. B and C, I have 2, that's 4. I have 4 kilograms down. That's 40 newtons of gravitational mg, 40 newtons of normal force from the floor. Once again, they balance out. They won't always. We'll get to that. Don't worry. Now, if I want to use F equals ma to figure out what the force is on this. So it's accelerating at 2. The whole system is. So this system is accelerating at 2. So 4 kilograms times 2, that means 8 newtons of force is what's being exerted on it right here. Now, that's being exerted by the normal force between this box and this box B. So now let's do a free body diagram for box B. Okay, here we go. So let's see what I know. I know box B has a mass of 2 kilograms, so mg is 20, and it's not sinking into the floor or accelerating upwards, so I know that the normal force from the floor is 20. I know that it is pushing, let's see, it's being pushed in this direction by box A, so that force is going in this direction. And I know that since it's pushing on box C, then box C must be pushing it in the opposite direction. That's the one you don't want to forget. So now what I got is figure these out. All right. So let's look at box C. All right. So box C is accelerating at 2, and it has a mass of 2. So the force on this one is 4. And so if this one is being pushed this way at 4, it is pushing backwards on this one with 4. All right. Now, how hard is this box pushing on B? Well, what I'm going to say is, all right, let's see. I know that 2 times 2 is 4 newtons. That's what it takes. That's how much net force it takes to make this accelerate at 2, right? So the net force, the sum of the force has to add up to 4 newtons. I know that I have negative 4 caused by the box C. So therefore, negative 4 plus the applied force, the box applied by A, is going to equal 4. So when I solve that, I get 8 newtons. And when I look at this now, 8 plus negative 4 is 4. 4 divided by 2 accelerates to 2. It works. Yay. Okay. Things hanging from strings. That's a big part of this course. You can almost call this course Things Hanging from Strings. All right, let's try this here. Each of these things has a mass of m, and I want to know what the value of tension force T3 on this string right here, just this one string here. Okay, so I'm going to just say, I'm going to collectively call this my system. It has a mass of 3m, so therefore the gravitational force downward is equal to 3 mg. And since it's not accelerating in the downward direction, it's tied to the ceiling, the upward force of tension force T3 must also be 3 mg. Draw a free body diagram for each object in it. Well, let's start with the one on the outside because that's the easiest. A is being pulled down with m. It has a mass of m, so it's pulled down with mg. It's not accelerating, so this tension force here must also be mg in the upward direction. Okay, sorry, scratch my ear, that's gross. Now, let's go to B. B is being pulled down by gravity, and it has a mass of m, so I have mg pulling down on B. But remember, tension force T1 was mg pulling up, so Newton's third law says, well, tension force T1 must also be pulling down with mg. So I'm going to label the downward one. Oh, whoops, I didn't mean to do that. I'm going to label that one T1. So they're both going this way. When I sum up the two downward forces, I get 2 mg, and it's not accelerating. So T2 pulling upward must be 2 mg. Now we're going on to this one here. It has a mass of m, is being pulled down by gravitation, so that's mg. T2, we calculated to be 2 mg pulling upwards on this one, so that means it's pulling downwards on this one with 2 mg. So I'm going to draw one twice as long, label it 2 mg, 2t. The sum of this is 3, so the upward force on T3 must be 3 mg, which is what we found before. Now we got an elevator problem finally. Okay, so, all right. Now we've got is a 4 kilogram box stacked on top of a 2 kilogram box in an elevator that's accelerating upwards at 2 meters per second squared. draw a free body diagram for each object. Well, let's start with the one on top. It'll be easier. Okay, so the one on top has a mass of 4, so I know that mg is 40. Okay, great. So I know mg is 40, and I'm going to call it the downward direction is negative, so it's negative 40. There's a normal force being pushed up on it between these two, the surface here, the 2 Gilbert boxes pushing up on it, with a normal force that I don't know what it is yet. But I do know this, that this 4 kilogram object is accelerating in the positive direction at 2 meters per second squared. So sum of the force equals ma. M is 4, A is 2, so that gives me 8. This is negative 40, so when I solve for this, I get 48. So the normal force between these two boxes is 48 in the upward direction. So I have 40, I have 48. When you sum those up, you'll get 8 in the positive direction. 8 divided by 4 will give me 2. Hey, it works. So now, last thing, let's check on the 2 kilogram box. Okay, what do we got here? Well, it's not that hard. We just have to keep in mind that there's this internal force that's got to go in both directions. So some of the forces are going to equal ma. Let's just start with this. I always start with this. I have an object that has mass 2, so mg is going to be 20. Got that. We just determined last time that the upward force on this box is 48, so there has to be an action-reaction pairing. So there's got to be a downward force of 48 also. There it is. Okay, now the thing is, the sum of the forces is going to cause a 2 kilogram mass to accelerate it too. So the sum of the forces, mg down, the normal force of the box, and the normal force on the floor are all going to sum up to make 2 kilograms accelerate it too. So I got 4 newtons here. I've got negative 20, that's the downward direction from mg. I've got negative 48, that's the downward direction caused by the normal force between the two boxes. And that leaves me just to find the floor. So when I say 4 plus 48 plus 20, I get 72 newtons of upward force. Okay, that was it. Thanks for watching. Sorry this one took a long time, but I'm glad you followed along.